Thank you, Frank.
Okay, I get it. No one likes to learn new stuff. Unless your name is Hermione Granger, of course, which I know that you don't exist. Anyways, limits are pretty important in learning calculus because it helps you understand whatever the heck is going on most of the times. Say, for instance, do you get what's going on here? Obviously not, right? Don't worry, you will get it in a minute. But before that, I'd like to thank our sponsor, Raid Shadow. Basically, a limit is the value a function approaches when its input gets closer and closer to a certain number. Limits can be taken from the positive side or the negative side, and are usually written like this.
Now you know what limits are, let's move on to function continuity. In a graphical sense, discontinuous functions are, well, discontinuous, and continuous functions are, well, continuous. In an algebraic sense, a function is continuous if and only if the limit taken from the negative side is equal to the limit taken from the positive side is equal to the value of the function at a certain number. Otherwise, it is discontinuous. Now that we're done with continuity, we can move on to the limit definition of the derivative.
Now, I know that this notation looks really confusing, but basically what this means is the slope between 2 points on a curve when the points get closer and closer together.
Or, in other words, the gradient of the tangent. Now, I know that the dividing by 0 here looks really intimidating, but trust me, this is a normal thing in limits, and you should be able to fix it. Just kidding, you can really fix it sometimes. But let's not worry about that for now. Anyways, when on the topic of limits, differentiation has 3 major steps. 1, you explain the functions x plus h to the power of whatever minus x to the power of whatever over h, and then you simplify the expression by cancelling out the terms. And then lastly, when the h is gone from the stupid denominator, you let h equal 0 and you get your answer.
Now take a look at these 3 limits. Notice anything? Yeah, they all follow this format.
Now, the proof of this power rule as far as whole numbers are concerned is relatively straightforward, but it involves a little bit of binomial theorem. Basically, the x to the power of n term in the binomial expansion of x plus h to the power of n cancels out with the x to the power of n on the right. After that, you can simplify the x from the expressions, but then you realize that every single term except n times x to the power of n minus 1 becomes 0 because they all have an h in it. For the sake of convenience, I'm only going to go over the natural numbers proof, but if you're interested, you can search up the other proofs as well. Also, these are the other derivatives that you actually have to remember, but due to a lack of space on the screen, and definitely not because I'm too lazy to do the proof myself, I think it will be best that you just search it up yourself. Now we're done with that, we can move on to the rules of differentiation. Now, these 3 are pretty intuitive, but these 3? No, they're just remember them, bro. And that's all I have to say. The end. Nah, just kidding, I haven't even covered everything yet. I think the main issue with these formulas are like people don't know when or how to use them. Don't worry, differentiation is actually a lot less intimidating than you think. Basically, if you see multiplication of functions of any kind, you use the product rule. The product rule is pretty simple. You take the derivative of one term, multiply it by the other term, repeat, and then add them up. Easy and straightforward. What is less straightforward, however, is the chain rule, and it is sometimes a little bit difficult to spot. Here you have to look for a function that is clearly inside of another function. Once you find them, you can apply the chain rule. Now the chain rule is a little bit confusing, but bear with me for a little bit. You have to substitute the g function into the x of the derivative of the f function, and then you have to multiply it by the derivative of the g function. Now, you may be wondering why I'm emphasizing the order all of a sudden, but it turns out that unlike the product rule, the chain rule is very dependent on the order. If you ended up messing up the order, well, you're dead. So let me repeat that again. You have to substitute the g function into the x of the derivative of the f function, and then you have to multiply it by the derivative of the g function. Now that we've got that over with, we can move on to the quotient rule. Basically, if you see any variables in the denominator whatsoever, you are going to use the quotient rule. Just like the chain rule, the quotient rule also cares about order, but you will have to be an absolute fool to mess up the orders of the denominator and the numerators, so it matters a little less. On screen right now are the ways to solve the questions given, and you can pause the video right now to take a look at them. Now you know how to find derivatives, let's take a look at how to use them. But before that, I'd like to thank our sponsor BetterHelp. I'd like to talk about differentiability. Now, the point at which a function is discontinuous is obviously indifferentiable, but with continuous functions, it is a little bit more annoying. In a graphical sense, a point is differentiable if it is smooth, meaning that if zoomed in enough, it should resemble a straight line. An indifferentiable point, however, will stay pointy no matter how much you zoom in. In terms of derivatives, it simply means that the derivative of the function is continuous at that point. Which is why this is differentiable for all x, and this is not. Now that we've got differentiability over with, let's get into how do we actually apply calculus. So, of course, teaching stuff is boring, and I think you already had enough of it. So instead, I'll make it a little bit more interesting by asking ChatGPT to generate a poem for me about applicational calculus, and I'll provide some visual aids along the way to help you understand what's going on. Now, let me present to you a calculus ode. Upon the curve where numbers stands, a point awaits its destined chance. To trace the tangent's fleeing grace, we delve into calculus's embrace. Given y equals f of x, at point A its value checks. First find m the derivative's might. Slope of the tangent line takes flight. With slope in hand, the path is clear. The tangent equation now appears. Y minus f of a left of the sign equals mx minus a behind. At coordinates where dreams reside, plug in the values side by side. The line emerges straight and true, a fleeting touch where curves renew. But normals seek a different way, perpendicular in their belay. Their slope, the negative inverse tells, a stance where right angles dwell. Thus, the normal's equation sings, a line that orthogonally clings. Take the tangent, but replace the m with its twin minus 1 over m. Upon the graph where shadows play, a curve unfolds in bright array. To find its peak and troughs below, we turn to differentiation's flow. Given f of x, we start a quest to locate the extrema at their best. First, take the derivative's hand, m, which is the slope's command. Set the first derivatives to 0 grace. M equals 0, find each place. Where slopes are flat, the journey deepens. In these points, the curve's hard leans. But not all solutions claim their price. Some points lie beneath disguise. To discern where highs and lows, the second derivative surely shows. F double prime x, the curvature's sign, determines if peaks align. If f double prime x larger than 0, revive. A valley forms where minima thrive. If f double prime x smaller than 0, ascend. A mountain's peak towards the end. Yet some points may simply stand, inconclusive without land. The first derivative test my aid to classify each point displayed. First derivative test revealed. Increasing to decreasing, a peak emerges worth believing. Decreasing to increasing, a valley forms serene and pleasing. So, when you stand upon the curve, with calculus your tool and verb, embrace the slopes, both steep and mild, and let equations reconcile. Phew, that's a lot of stuff to cover. But anyway, we're done with calculus. Right? Right, guys?